There's something that shouldn't exist anymore. By every rule we understand, it should have disappeared a long time ago, worn down, broken apart, replaced by something better. But it didn't. It's still there. Not because it was repaired, not because it was protected, but because it was built in a way that doesn't rely on either. And that creates a problem. Because if something like that exists, then everything we build today might be missing something fundamental, something we stop thinking about. If something can survive that long without constant repair, without modern materials, without the systems we depend on today, then the question isn't how impressive it is. The question is, what did they understand that we don't? Because most of what we build now follows a completely different logic. We design for performance, for speed, for efficiency, for immediate results, but rarely for permanence. And that changes everything. Because when a system is designed to perform well in the short term, it usually depends on something else to keep it working over time. Maintenance, energy input, replacement cycles. And once you depend on those, you're no longer building something that lasts. You're building something that needs to be constantly saved, which works until it doesn't, until something interrupts the system. Supply chains break, resources run out, conditions shift, and suddenly, what felt stable starts falling apart faster than expected, not because it was weak, but because it was dependent. Now, here's where it gets interesting. The thing that survived all that time wasn't designed this way. It didn't rely on constant input. It didn't need to be preserved. And it didn't fight the environment the way modern systems do. It did something else entirely. It worked with it. Or more accurately, it removed the parts of the environment that cause failure in the first place. Because most systems don't fail from one big event. They fail slowly, from the inside, from processes you don't notice until it's too late. And almost all of those processes start in the same place, not above the surface, but below it. The failure doesn't begin where you think. It doesn't start with pressure, or weight, or time. It starts in the ground. Because the ground isn't stable. It looks solid. It feels reliable, but it's constantly changing. Moisture moves through it. Temperature expands and contracts it. And more importantly, it's alive. Tiny roots push upward, searching for space. Insects dig through it, creating invisible tunnels. Microorganisms break down whatever holds it together. And none of this happens all at once. It happens slowly, quietly, layer by layer, until the surface above it starts to shift. Cracks begin to form, not from impact, but from instability underneath. And once that process begins, you don't stop it. You manage it, you repair it, patch it, reinforce it, again and again, because the system itself has already started failing. A modern engineering understands this. That's why we constantly resurface, rebuild, replace, because we're not eliminating the problem. We're keeping it under control. But control has a cost. It requires time, resources, energy. And the moment that cycle breaks, the system accelerates toward failure. Now imagine approaching this from a completely different angle. Instead of asking, how do we fix damage after it appears? You ask something else. How do we stop it from ever starting? And that question leads to a very different kind of solution. Not stronger materials, not thicker layers, but a change in the foundation itself. Because if failure begins in the first layer of the ground, then that's the only place you actually need to act. They didn't build on the ground, they transformed it. before anything else was added, they removed what made it unstable: moisture, organic life, movement. The goal wasn't to reinforce the surface, it was to change the behavior of the material underneath. Because once you understand what causes degradation, you don't need to fight it. You can eliminate the conditions that allow it to exist. So they started by digging down to a stable layer, not just compacting what was already there, but reshaping it. And in some cases, they used heat, not to build, but to destroy. Fires were applied directly to the ground, sustained long enough to drive out moisture, to burn organic material, to disrupt everything that allowed life to exist within it. And something interesting happens when you combine heat and pressure on soil. Water disappears, organic matter breaks down, and the fine particles, clay, silt, begin to lock together, tightly, densely, until the ground stops behaving like soil and starts behaving like something else, something closer to a solid structure than a living system. But that was only the first layer, because removing instability isn't enough on its own. You also need to prevent it from coming back. So above that, they added compressed layers, thin sections of earth packed down repeatedly, each layer increasing density, reducing air gaps, limiting movement, until the surface became almost resistant to change. Not invulnerable, but controlled. And then, they addressed the one thing that always finds a way through: water, because water doesn't force its way in. It waits, it settles, it collects in the smallest imperfections, and over time, it breaks everything apart. So instead of blocking it, they redirected it, shaping the surface so water couldn't stay, guiding it away before it had time to act. 3 decisions: remove life, increase density, control water. And with that, the system stopped behaving like something that needed maintenance and started behaving like something that could last. At this point, most systems would still have one problem. Even if you stabilize the ground, even if you control water, the surface still wears down, because anything that's used eventually degrades. Pressure builds, friction takes effect, movement breaks structure apart, and over time, that damage accumulates, which is why most modern systems are designed around repair. You expect damage, so you plan for it. But this system didn't follow that logic. It did something unexpected. It turned usage into reinforcement. Because the road wasn't just built for movement, it was built for repetition. Every cart that passed through followed the same path, not randomly, not loosely, precisely. The width of each axle was standardized, so every wheel fell into the same position, again and again and again. And at first, that seems like a flaw, because repetition creates grooves, ruts, tracks carved into the surface, and normally, that's damage. But here, it wasn't, because those repeated movements did something else. They compressed the surface, further, deeper, tighter than any initial construction could achieve on its own. Every pass added pressure, every wheel increased density. And over time, the surface didn't break down. It hardened. The more it was used, the stronger it became. And there was another effect. The edges of those tracks were constantly scraped, smoothed, refined, irregularities removed with every rotation. The system didn't just resist damage, it corrected itself, continuously, without intervention, without maintenance, without anyone needing to stop and fix it, because the users themselves became part of the system. And that changes everything, because now, the system doesn't degrade under stress, it improves. But a road that maintains itself is only part of the solution. Because movement isn't just about surface, it's about continuity. Speed isn't defined by how fast something can move. It's defined by how long it can keep moving. And that's where most systems fail. Because no matter how strong the structure is, the limiting factor is always something else. Energy, fatigue, biology. In this case, horses. A horse can move fast, but not for long. Push it too far, and it stops. Push it further, and it collapses. So the question becomes not how fast can you go, but how do you never have to stop? And the answer was not in the road. It was in the network. Instead of relying on endurance, they broke movement into segments, short distances, measured intervals, each one connected to a fixed point, a station where everything resets, fresh horses, supplies, rest. Then movement continues, not slower, but sustained, over distance, over time. And when you connect enough of these points, something happens. Speed becomes consistent, predictable, scalable. Information moves faster than physical limitations should allow. But there was another layer to this: control. Because every point in the system was also a checkpoint, monitoring movement, tracking flow, observing everything that passed through. The road wasn't just infrastructure, it was oversight, a system that didn't just enable movement, but controlled it. And behind all of this was something even more complex. Because building the road was only the beginning. Maintaining movement required something else entirely. Supply. Thousands of people, distributed across vast distances, each one needing food, resources, support, and instead of building a separate system to sustain that, they used the road itself. As it expanded, it fed its own construction. Finished sections became supply lines. Supply lines extended the system further, a moving front, constantly advancing, supported by what had already been built. The system didn't wait to be completed to become useful. It functioned while it was still being created. But all of that only works on stable ground. And eventually, the ground ends. Mountains rise. Cliffs form. Terrain becomes something you can't build on. And at that point, most systems stop because there's nothing left to work with. No surface, no foundation, no path forward. But instead of stopping, they changed the problem. They stopped asking, how do we build through this? And started asking, how do we use what's already here? Because even the hardest materials have limits, not from force, but from behavior. Stone expands when heated, contracts when cooled, and when those changes don't happen evenly. Stress builds internally until the structure can't hold itself together. So instead of cutting through the mountain, they made it break itself. Heat, time, expansion, and then a sudden shift, a drop in temperature, a change the material couldn't absorb fast enough. And the result was failure, not from impact, but from imbalance. Sections split, fragments separated. The mountain didn't get carved, it got destabilized. And once that process began, they guided it, controlled it, shaped it into something usable. But even that wasn't enough, because eventually there's nothing left to shape, only empty space, vertical drops, gaps that can't be filled. And this is where the system becomes something else entirely, because instead of building on the ground, they built into the structure itself, anchoring directly into solid rock, extending outward, creating support where none existed before. And the more weight those structures carried, the more stable they became, because pressure didn't weaken them, it locked them in place. Now the system adapted not by resisting force, but by redirecting it. By now, the structure could survive. It could support weight. It could handle movement. But there was still one problem left: binding. Because no matter how strong individual components are, if the connections fail, everything fails. And traditional materials had limits. They were rigid, brittle, prone to cracking under stress, especially over time, especially under changing conditions. So the solution didn't come from engineering, it came from something unexpected: food. Because what they needed wasn't just strength, it was adaptability. A material that could hold form, but still absorb stress. That could resist water without breaking apart. And somehow, they found that balance in something simple: cooked grain. When combined with mineral compounds, it didn't just fill gaps. It changed how the material behaved. It bonded differently, responded differently, resisted breakdown in ways traditional mixtures couldn't. And the result was something that lasted far longer than expected. Not because it was stronger, but because it was more stable under change. And this is where everything connects, because when you look at it as a whole, this wasn't just construction. It was a system designed around reality, not ideal conditions, not controlled environments, but the actual behavior of materials, of movement, of nature itself. And that leads to an uncomfortable conclusion, because when modern systems approach the same problem with better tools, more data, more advanced technology, they often arrive at the same answers, the same paths, the same routes, the same decisions, not because they copied them, but because the constraints haven't changed. Gravity hasn't changed. Material behavior hasn't changed. The cost of movement hasn't changed, which means the solution hasn't changed either. It was already found a long time ago. And what we're doing now isn't discovering something new. It's rediscovering something we stopped paying attention to. So the real question isn't, how advanced are we? It's something else. What are we building today? That will still make sense 2,000 years from now, because the systems that last aren't the ones that perform best. They're the ones that don't need to be saved.